So, yes, Venus, of course, is that big bright object we see there. It has been known for a long time, and in fact, since time immemorial, dating back to as far back as the ancient Sumerians, we've actually had some indication that the planet that we see in the sky, this star that appears both in the morning and the evening, were actually one object, and they would have recognized that back in around 3,500 years ago, though there might be some debate on whether or not they fully understood that. They associated that bright object in the morning and evening with the goddess Inanna, and there is a story called Inanna's Descent in which she descends into the underworld and rises again afterwards, after being redeemed by a few other deities. But the main note is that some of the motions of Inanna in the sky, as they would be referring to Venus, might correspond to that particular story. That is at least what is being mentioned, because Venus doesn't end up very high in our sky. It only gets about, less than 50 degrees separated from the sun, so it is always either following the sun down to the horizon or leading the sun up from the horizon in the morning. So what would they actually see? Well, if you watch this particular object from night to night, you will watch it decently high in the sky, but working its way back to the horizon, and then it will set right when the sun does and will not be visible for a period of time, which would be associated with Inanna entering the underworld, as it were, and then potentially only a few days or even a few weeks later, you might spot Inanna again rising in the morning after that, before the sun. And so that is how you get that particular story associated with the planet Venus. Of course, there might be some debate in the archaeological community on that particular notion, but there is still a good amount of evidence to suggest even the ancient Sumerians knew that the morning and evening star were in fact one object. And Inanna is known by another name in a few other cultures. In the Akkadian, the Babylonian, and the Assyrian cultures, they referred to this goddess as Ishtar, and it was one that actually we'll come back and visit a bit later, that particular name. The Chinese also noticed this object, the great white object in the morning and the excellent west one in the evening. These big bright things are really nice and dramatic, and even the ancient Greeks saw this, and the main person associated with our modern day notion of the morning and evening star being actually one object, it really comes from Pythagoras, which would have been around the time of the ancient Greeks. Thus, the ancient Greeks start by referring to them, to these objects as Phosphorus and Hesperus. But again, it's one object, and it took Pythagoras to really figure that out. And heading on a little bit further, the ancient Romans knew it was one object, but they still used two names, one of which was Lucifer. Yes, Lucifer, though associated often with Satan in Judeo-Christian circles, it actually comes from a particular scripture that actually references something associated more analogously with the morning star, and thus the Roman translation of that ancient biblical text puts it as Lucifer, or light bringer, which corresponds to the ancient Roman name of the morning star. And likewise, the evening star was Vesper. But again, the names there are both literal translations of the Greek names, the Phosphorus being light bringer. And in any case, moving right along, we also had that in the 2nd century, Ptolemy was actually able to somewhat correctly at least surmise that Venus and Mercury both resided between the sun and the earth, though he got a lot of other things wrong, most notably putting the earth at the center of the solar system. Anyway, that's a whole other subject, because we can advance to where Ptolemy's model failed, and that was with observations of Galileo, who was the first to point a telescope at the object, and he noticed something really specific when viewing this object through a telescope. He saw phases. And when we're looking at an object like Venus through a telescope, we get to see a few specific things. When Venus is at its furthest point from the sun, it ends up being about halfway lit up. And when it's closest to the sun, it is either in nearly full or very close to its crescent phase. And when it's at its brightest, it is actually at its crescent phase. And Galileo didn't just notice phases, he also was very careful to measure the sizes of the apparitions as he saw them. For example, he was able to see this as it's shown here. When Venus is on the far side of the sun, it ends up appearing very small, but as it circles back around here, it gets nice and large. And then afterwards, it would be essentially a mirror image of this as it returns to a full phase as Venus moves around to the other side of the sun once again. And thus, by looking at the sizes and the phases, he correctly surmised that Venus was in fact orbiting the sun, not revolving around the Earth. And so, yeah, this was one of the main direct ways he said that the observations do not agree with the Ptolemaic model of the geocentric model of the solar system, and among other things in the way he actually handled things with the Roman Catholic Church, this was part of those problems that eventually led to his house arrest. But that, again, is a very detailed story. But moving right along, though, yes, we can talk in detail about all sorts of things about this planet. There are a lot of different facts and figures to discuss, so we can jump right through them. We got second planet from the sun, second brightest object in the night sky after the moon, which thereby makes it the third object that is brightest in the night, in both the day and night skies, again. Anyway, you can also see it under certain conditions during the day, under the right conditions. It is, again, a planet that is often referred to as Earth's twin, and that is because it's similar in size, mass, and proximity, and even composition. All those things really suggest that it should be somewhat similar to the Earth in many ways. Well, we'll see that it's not. But in any case, yes, it is also the planet with the densest planetary atmosphere, with 96% of it being made up of carbon dioxide. And in fact, it is also encased in a lot of clouds. Again, we'll talk more in detail about these, but they are highly reflective and also made up largely of sulfuric acid. And the atmospheric pressure at the surface is way higher than what we have here. Again, at about 92 times the Earth's surface pressure. It is not pleasant. It's somewhat equivalent to being 900 meters below under the surface of water. So if you went deep diving, you could experience this pressure, though really you wouldn't want to because it'd probably kill you. So you'd want a submarine at that depth, a very, very well-designed submersible, in fact. And the surface temperature there is much hotter than here in the summer. So yeah, that's saying a lot, but it is around 463 degrees Celsius on average, and that is in fact hot enough to melt lead. So again, substantially warmer than here in the summer. But in any case, it does actually lack something that the Earth has, and it is in fact lacking a magnetic field, one that would have actually been potentially helpful in keeping water on this planet, because water molecules could actually make it into the upper atmosphere where radiation from the sun can actually photodissociate them, break apart the water molecules into hydrogen and oxygen, and hydrogen then can get blown off the planet, leaving behind oxygen, which can then combine with CO2 to further insulate the planet in more greenhouse gases. Again, 96% of the atmosphere there is carbon dioxide. It's a lot of stuff there, moving right along. But underneath those clouds, we can see some interesting things. And underneath those clouds is a planet, of course, that is moving around the sun, and it takes it about 224 Earth days to make its way around the sun. However, its rotational period, that is how long it takes for it to rotate on its axis, is actually longer at 243 days, and that difference is really interesting. It causes some very interesting things to happen with regards to the day-night cycle on Venus. And what that also means, again, is its sidereal day is longer than its year. What is a sidereal day? It's the time it takes for one star to rise at one point all the way until it rises the next time. So that is how we're talking with a sidereal day. Those aren't that different here on the Earth. They're dramatically different. on Venus because a solar day here on the Earth is 4 minutes different than the sidereal day. That is, the time it takes one star to rise to the next time that star rises is one sidereal day. The time it takes the sun to rise to the next time that it takes the sun to rise is one solar day. And on Earth, it's 4 minutes different. On Venus, one solar day is actually much shorter than one sidereal day at 116.75 days, roughly. And so that's a really interesting fact that the solar day is shorter than the sidereal day, and in fact, again, shorter than its year. And that comes largely because the actual direction of Venus's rotation is what we call retrograde, meaning it actually rotates the opposite direction to basically all of the other planets if you're looking down on the North Pole. If you're looking down on the North Pole of the Earth will appear to rotate in a counterclockwise fashion. If you're looking down on Venus, it will rotate in a clockwise fashion, but again, it does so very, very slowly. Now, there's two possible causes for this particular rotation. One has to do with the fact that we have a very thick atmosphere there, and the idea that it produced a lot of friction and tidal forces that would eventually cause it to slow down and potentially rotate the other direction. Though the more accepted theory is that it probably got smacked by a big giant object that actually completely changed the dynamics of that planet, causing it to actually rotate in slightly the other direction, and again, very slowly. So it's a really interesting planet, and again, it's almost like the Earth's twin. It is very similar in diameter and as well as mass. And there are a lot of features there that are similar to the Earth. There are, of course, volcanoes and some geologically recent activity. Again, the sulfur in the atmosphere is a good indication of volcanic activity. We find a lot of sulfur deposits and sulfur gas release around volcanoes here on the Earth. But again, it doesn't have oceans. And while it doesn't have oceans, we can still see sort of things we could refer to as continents, really these highland regions that would, if there was an ocean, they would sit above if you filled it up just right. These would be your continents, kind of like what we see on the Earth. But again, there isn't an ocean, so it doesn't really look like they're there. The main ones you can see are Ishtar Terra and in the north, and Aphrodite Terra. Aphrodite is this big, funny, long region right here, and Ishtar is over on the back side right over here. Over on this side right here, where we have a nice picture of Maxwell Montes, a nice mountain. But again, Ishtar Terra is roughly the size of Australia, while Aphrodite Terra is roughly the size of South America. Again, in a much more elongated, squashed fashion. But again, the highest peak on Venus is that Maxwell Montes, and it's up in Ishtar. It is really one of those big shield volcanoes, and it actually has, again, around an 11-kilometer average elevation above the general surrounding terrain. And what we're looking at here is actually the corner or the edge of that mountain where the big white feature there on that globe really is highlighting most of the rest of the mountain. But the rest of the surface of Venus is really interesting when you actually get a close look at it. 80% of it is smooth, with 70% of that being little wrinkled plains, little ridges you can find. It has all sorts of apparently what look like stretch marks all over it, and a number of the remaining 10% there of that 80% is actually very smooth. There are a lot of volcanoes there, and there are a lot of big ones, of course. 167, more than 100 kilometers across, and that also leads us to an interesting thing. Well, if we can see volcanoes, can we see impact sites? And yes, we can see a few, but they look a little different, and there aren't very many of them. And there's a few reasons why there wouldn't be many of them. Again, there is a dramatic, very thick atmosphere there, and as things enter atmospheres at high velocities, they burst into flames. And that is why we see many shooting stars, but don't find all that many meteors compared to the number of shooting stars we see. Likewise, a thicker atmosphere will actually cause larger objects to potentially explode on entry, leaving fewer craters that way. However, even with that taken into account, there's still not enough in the way of impact craters to suggest a very old terrain for Venus, especially given there does not appear to be a lot of erosion going on, mostly just volcanic activity. So it leads to a possibility that, well, what if the surface of Venus didn't do what we have here on the Earth with a nice constant change in the surface structure? What if it actually completely turned over somewhere between 300 to 600 million years ago and the entire planet basically resurfaced? That's one possibility, but all of that volcanology, it's worth talking in detail more about those volcanoes. And yes, this particular planet has more volcanoes than any other planet in the solar system, with over 1,600 volcanoes and more than 1,000 volcanic features. Again, this planet may have actually had a full overturning of its surface sometime in the last 300 to 600 million years, and it may happen roughly every 500 million years. So this, again, is largely based on that density of impact craters and the fact that they aren't really set up in a way like we see on the moon, with some regions having lots of craters and some regions having almost none. No, we see them pretty distributed largely evenly over the surface of the entire planet. So yeah, well, what is going on there might have been a full overturn. But there are plenty of volcanoes that we see there that are really unique to this planet, or at least relative to what we've seen in the solar system. There are plenty of volcanoes we don't see here on the Earth, including things like arachnoid surface features, things that are volcanoes that actually might look a bit, if you look at it under a certain lens, as it were, a bit like a spider web. You can see all sorts of different features with concentric rings and radiating cracks and other features heading in there. The details of how exactly these form are, of course, under study continually, but this might be more like a blister, as it were. And again, they can span some dramatic regions, about 200 kilometers in many cases. And I will note, when I was actually going to find where these objects were on the planet, I actually found some loose directions on where they might be on the planet, and then I went and actually found exactly where they were. And so these objects being 200 kilometers across, this one was really easy to find. But again, you can spot these things quite easily on that full globe of Venus. And other things we can spot on Venus include tick-like structures like this, which would be basically a type of shield volcano. And the shield volcanoes on the Earth, most of them are relatively small. There are a few larger ones, but most are only on the order of a few kilometers wide with 10 kilometers high. On Venus, many of them, again, are hundreds of kilometers high, but they also tend to be relatively flat. And things like this particular tick shape, which is again referred to as a scalloped margin dome, as in the edge of the dome appears scalloped like a doily, I'd say. In any case, that particular shape, we don't see this type of volcano looking specifically like this here on the Earth, not with a main dome with the outside edge being scalloped like that. And often these types of things on Venus do have a little bit of a depression in the middle, but again, this isn't one of the ultimate of the weird things we find on Venus. There are plenty of weird volcanoes. And then among the last ones that I want to go into are these ones, which all I have to say is, pancakes. Yes, these pancakes are really interesting features that show up in all sorts of places. They really are set up like big pancakes. In this case, you can think of it a bit like it looking like a shield volcano in the sense of the way Mauna Kea looks. It is a volcano that formed under very different circumstances, but in any case, that big, broad, flat, curving shape that we see at Mauna Kea is somewhat similar to these. And these things are found in a variety of different places on Venus, and they often are found together. And really where you find them is where there's a lot of activity around them. That is, they might be in some of the flatter areas, but there might be some really dramatic shifting of the terrain around them. And they are quite large, again, 10 to 100 times larger than volcanic domes here on the Earth. And really, when you're trying to think about how these pancakes will have formed, it's kind of like what you would see if you're making pancakes. You pour your pancake in the pan, and it expands outward. It then solidifies in that particular space there, by and large. But instead of it being poured onto a pan here, it's more like it's breaking through the surface and oozing out over time over on top of itself. And then eventually the top solidifies, leaving that nice cracked view, sort of like what you can see sometimes in your pancakes. In any case, that is really what we're looking at as a long, slow eruption. And I just really love these things. I want some pancakes now. I'm sorry if I'm making you hungry. I'm hungry. But anyway, Venus itself does have a unique interior. However, that interior, while I can show you this nice fancy cutaway here, it's largely unknown to us. It's largely unknown to us because we've never been able to put a seismometer on the surface to really get good interior, basically sonography. The way we actually know the interior of the Earth is by having these seismometers scattered on a number of different places around the Earth. The waves from different earthquakes or eruptions or other activities will send shock waves through the planet, and we can actually see how those shock waves reverberate around the inside to determine what's going on the inside. We can't do that right now with Venus because we don't have the equipment there to actually make those measurements. So what we're actually left with is largely starting with what we know of the Earth. Again, as they are twins, this is at least a start. It may not be ideal, and it is somewhere to start. And so we end up with something like a crust, a mantle, and a core arrangement. Again, if you know the Earth's geology, you know that even this is a vast oversimplification on what's going on beneath our feet. So if we're starting with a vast oversimplification for the Earth with talking about a crust mantle core, well, at least we're probably not too far off the mark for Venus since we really don't know what's going on there. But we do expect that the core of Venus is probably at least partially liquid, again, because if we're looking at the Earth's core, it has a partially liquid core, and so comparing the two, you would expect, again, given similar cosmological time for these two worlds, that the actual heat dissipation would lead to also a somewhat liquid core. However, again, at over 80 or around 80% the mass of the Earth, the less mass means there's actually less pressure at the core, which can result in some interesting things, potentially. But one of the big things we can see when we look at Venus is, of course, the surface. Although we can't see it directly, we again are using radio imaging. But with those radio imaging images, we can actually learn some things about what's going on there. And what we do find is a lack of plate tectonics. Things we have here on the Earth that are really important to how our whole Earth is shaped, where different mountain ranges are, where different oceans are. All of that has to do a lot with plate tectonics. And the lack of plate tectonics, whether or not it is a driving factor or a result of a particular thing going on the interior, it does lead to a potential link, and that is if there's no plate tectonics, well, the surface itself is in essence less viscous. That is, it is not able to move over itself all that much, and it might also therefore emit less heat, and that means there's probably less ability for an internal magnetic field to be generated, because actual movements of things on the inside of a planet really do help drive the actual magnetic fields of a planet. Again, we have a dramatic magnetic field here at the Earth, and that is largely due to the motions of, in our case, a lot of metals deep inside our planet. So, without a significant amount of motion, which might be driven by a lack of actual thermal loss, that is, driving motion of that particular region inside the planet, well, you don't end up with much of a magnetic field. And that is really important, which we'll come to. And we'll come to it as we talk about the clouds. Again, it is, in fact, always cloudy on Venus. Its atmosphere is, as I mentioned, extremely dense and made up largely of carbon dioxide. And the atmospheric density at the surface is around 65 kilograms per square meter. You say, okay, whatever, but 50 times what we have here. Put it into perspective. 1 meter might be about, this on a side. Take a box 1 meter on each side and put me in it, and that would be roughly the weight of the atmosphere in that volume on Venus. That is not too different from me. So that is a lot of air crammed into a small space to give that kind of density. But this particular atmosphere being made up largely of CO2 means it actually retains a whole lot of heat. And thus, these surface temperatures on Venus are higher than Mercury. If you were here a couple of months ago when we talked about Mercury, you would have caught that, or maybe you wouldn't have caught it. It's a long time to remember one little fact or figure. But in any case, it is a dramatically hotter place than the planet that is closest to the sun. And because it has a lot of insolation, that temperature is fairly constant around the planet. It doesn't matter if you're on the day side or the night side. Just like if we have a lot of clouds outside here, if we have a cold day and clouds roll in, and then through the night we actually have clouds all that time, it's going to be cold. But if we have a warm day under clouds and those clouds remain through the night, it'll be a warmer night. If we have, again, a warm day and then a night with no clouds, it will end up being colder. That is one of the frustrating things about stargazing at times is the best nights for stargazing are often the nights where it's really chilly out because, well, we'll start with a nice day that was nice and warm, and then with no clouds up, all that heat that's collected during the day gets dissipated and we end up with a really chilly night. Then you compare that with the nights we can't stargaze, and it's perfectly comfortable outside, even if the day started the same temperature. Anyway, frustrations of an astronomer. Moving right along. All right, so with the temperature, what you see is what you get. And the surface of Venus, really, again, the day and night side are roughly equal in temperature, but it goes beyond that because if you go even from the equator to the poles, there's still a fairly stable temperature there. And given that the rotation of Venus is slow, it's also worth noting that its axial tilt, the thing that causes the seasons here on the Earth, because the Earth's rotation axis is tilted 23.5 degrees relative to the plane of its orbit, Venus's axial tilt is about 3 degrees, or 177 if you want to actually think about it still rotating the same way as the other planets, just being flipped over. Anyway, there's some fun debate in the astronomical community on which way you want to look at that. But the idea there, though, is that the seasons are essentially non-existent on Venus because there's no significant axial tilt relative to the orbit of the plane of the planet's orbit. And so, you aren't going to get any significant seasonal fluctuations. And while if you go dramatically higher in the atmosphere of Venus, you'll see some temperature change, if you're going around like we can here, where we can look up to some mountains and see some snow up there, changing your altitude, driving around Venus, you're not going to get much of a different temperature change. It's, of course, substantially detectable, but even if you go to the highest point there, the mountains up there, they get to a nice chilly 380 degrees Celsius. Very, very hot still up at the top of the highest mountain there. So you have to get up to around 50 kilometers up before you start getting temperatures that we might be more used to. And with that actually comes some interesting things with regards to the pressures there. The pressures there actually aren't that far off to what we are used to. But that height comes with some other things, because as we go up, we find ourselves with a lot of clouds again, and those clouds are made up largely of sulfuric acid. you thought that ground was bad. Yeah, sulfuric acid, not fun to deal with, especially with your spacecraft. But when you're talking about sulfuric acid, one of the ways you can get it is with interaction of sulfur dioxide and water. And again, about 1% of that atmosphere in that area is a ferric chloride, which again, not going to be a fun thing to deal with. But the clouds at different altitudes, yes, they do have different chemical compositions, so you end up with a further complication on your way around the atmosphere there. And these are those clouds that reflect a lot of that sunlight, and that reflection of sunlight really is important for more the history of Venus, or I should say the Earth viewing history, because by reflecting a lot of sunlight, that is why we see this thing being so bright in the sky, why it earns that name as the morning star and the evening star. But those clouds, again, it's interesting to note, as they are very good at reflecting a lot of sunlight, they're also, once again, important for the insolation of the planet. And thus, despite the fact that the planet actually only absorbs about 10% of the sunlight that falls on it, it's still retaining so much of that heat that it is incredibly hot. It's just interesting with regards to that greenhouse effect. And so with all those details, trying to get down to the surface of Venus is a interesting proposition. Often we will prefer to stay in the orbit above Venus, and in fact, that globe you saw me working with there, that was one made, of course, from orbit, but we do have some images of the surface like this one here. And yeah, Venera 9, it got to the surface, and when it got there, it had to deal with all these different challenges. Again, the very high temperatures that can melt lead, the surface pressure that is like being nearly a kilometer underwater. That sulfuric acid in the atmosphere is not friendly to your spacecraft. And again, being deep under all those clouds, you got to get creative with your solar panels if you want them to generate any electricity. And at this point, we haven't actually gotten creative enough. So no spacecraft that have landed on the surface have generated power through solar panels. And in fact, the longest lasting rover there only sent data back for about 2 hours. It's, again, Venera 9's image is one of the few images we have of the surface directly. And yeah, that's black and white image, so who knows what color it is. Now, there's another image that we do have, though, that gives a little bit of a hint on that color, which is more of the more of that sort of sulfury kind of color. But when we're talking about going to Venus, it's good to go back and see in detail all the different things we've actually used to get there. And we've done a few different routes over the decades. Starting back in the 1960s and 70s, there were a lot of missions, specifically a lot of Soviet missions especially, but there were U.S. missions in the Mariner program and even some joint data analysis from those two programs, along with another mission from the U.S., which was the Pioneer Venus program, which had a number of interesting things, which I'll talk about in a minute. Fast forwarding into the 80s and 90s, we do have Venera and VeGa, where it's sort of a rebirth of that Venera program, but specifically for a joint object mission. Again, get to that in a minute. And then there were a number of gravitational assists, that is, spacecraft flying by Venus to get a little bit of a kick. And so Galileo, the Cassini-Huygens mission, both of those missions used Venus for some nice extra boost out into the outer solar system. And then in the 2000s, there were a couple of other missions. The Messenger spacecraft was on its way to Mercury, and it used Venus for a gravitational assist. Rather than a slingshot to give it energy, it used Venus to take away some of that energy and bring its orbit deeper into the center of the solar system. And then there was Venus Express and Akatsuki, which, again, those are really interesting. Akatsuki is still operational, but it's the only spacecraft there right now. Again, more on that and Venus Express in just a minute. First, back to Venera. Venera is the Soviet Union's main Venus program. It went for quite a while, and they sent plenty of probes into the atmosphere, with 10 actually reaching the surface. And again, some of these actually transmitted back for a little while. 23 minutes is a good start. 2 hours, yeah, it's pretty impressive for working there. But again, it's really a challenge to get there. And by the way, along the way to talking about Venera, it's important to note that Venera is basically Russian for Venus. But the real big things to note is while they may have only operated for brief periods on the surface, the Venera program had a lot of really important accomplishments, including the first human-made devices to actually enter the atmosphere of another planet. That was a Soviet mission. Again, Venera 4 would have done that. And also the first to do a soft landing. Interesting to note that, these weren't the same mission. Again, entering an atmosphere and reaching the ground, two different things. And that was something that they designed into them along the way. But again, we also got the first photos of another planet's surface through this mission. By that I mean not just, oh, there's a globe of Mars, we got a picture from Mars. No, I'm talking about a picture from the surface. This was the first one to do it. And again, they also did their high-resolution radar mapping of the planet there, and we got a lot more of that radar mapping along the way, which gave us a lot of really interesting things. Now, the VeGa mission is actually one that is a joint mission from a number of different countries, mostly led by the Soviets, but also with a bit of collaboration with Europe. And there were a number of things with regards to those probes. They were aiming for two things. They went with two ballooned crafts that were sort of deposited on the way past Venus to actually descend with balloons to actually slow their descent down to the surface. And then the rest of the spacecraft didn't go into orbit around Venus. It actually flew on to Halley's Comet, which it made it there in 1986. And the name, if you notice that capital G, it's coming from Venera Gali, or in the case of Russian being Venus and Halley. So a fun little note on the name there. On to this side of the planet. Our missions here really started largely with the Mariner program, and there were a number of different Mariner missions to Venus. 1, 2, 5, and 10 actually made it to Venus, and a number of them were actually, or rather, I should say, these were aimed at Venus. They didn't all make it. Yeah, one kind of blew up on the way. But it's still worth noting that most of these made it. Mariner 2 did actually go and get some good measurements of the temperature and magnetosphere there. Again, that rather empty magnetosphere by and large because it does not generate its own magnetic field. And again, Mariner 5 furthered those measurements. And then Mariner 10 was a really interesting one because it didn't just fly by Venus and say, okay, we did our job. No, it actually flew by Venus and Mercury, and that's a really important detail for what came next, because again, these accomplishments from the Mariner program really highlight what we learned with it, because Mariner implies someone who is able to sail, and this was where we really learned how to sail the seas that are between the planets. And so we had our first planetary flyby with Mariner, we had our first planetary orbiter, and our first gravity assists. The reason why there isn't a Mariner 11 and 12 is because we learned so much with the Mariner missions that we called 11 and 12 Voyager 1 and 2. Those missions, again, used data from specifically largely the Mariner 10 flybys of Venus and Mercury to really utilize gravity assists out in the outer planets to get the Grand Tour, as it's often referred to, specifically for Voyager 2. And those two spacecraft are now out in what we refer to as interstellar space. It is out beyond the heliopause, the point at which the radiation from the sun is met by the radiation from the rest of the universe. So by radiation standards, yeah, they're outside the solar system, which is a wonderful feat, and we're really happy that they're still kicking. But after Mariner came the Pioneer Venus project, which had two probes. There was, of course, the orbiter, which actually was able to study the atmosphere and the surface in good detail, and it worked for quite a while, again, from being in orbit in 1978 all the way to 1992. And then there was the multi-probe section of the mission, which actually put 4 small probes into the atmosphere, and they sent data while descending, which is great, and one even survived landing and sent data for an hour. That's pretty good. Yeah, that's really quite an accomplishment at Venus to have anything not only reach the surface, but actually last for anything more than a couple minutes is impressive. Then we have the European Space Agency's Venus Express mission, and it was really their first Venus mission, and it went in 2005. It was quite a successful one because it was doing long-term studies, which meant it was able to gather a lot of data, and it would even really help us understand in general, well, again, things like greenhouse gases and how they work with sunlight. So it actually helps us understand some things going on here on the Earth right now. And it actually had an interesting orbit. Rather than orbiting around the equator, it actually had a polar orbit, which allowed it to get full coverage of the entire planet, and including looking at a number of interesting things in different parts of the atmosphere. There's some interesting little vortexes at the poles that are visible, and the Venus Express was what actually allowed us to see that. And more details, it actually launched from a site that was formerly in the Soviet Union, and it actually arrived not that long after, again, less than a year to go from launch to arrival, and its polar orbit wasn't circular, it was much more elliptical, taking it between, again, 266,000 kilometers, 250 to 66,000 kilometers from the surface of Venus. And so that big sweeping motion gives a few extra little details because it allows you to explore different parts of the region around Venus. Again, really important for our studying that magnetosphere that really is not exactly there, but that doesn't mean it's not worth studying. And it actually conveniently took 24 hours to do one orbit, which was probably really convenient for anyone here on the Earth working with the program. They actually could work on the same clock as the spacecraft and make sure they saw the exact same patterns. But they looked for interesting things with that. They actually turned some of their instruments back to Earth to actually look at the Earth's atmosphere to see if they could find signs for life, because that's useful for trying to figure out if we could do something similar looking at other planets outside the solar system. But of course, its main study was for looking at Venus's atmosphere, again, the clouds, the plasma environment around it, and other surface features. And one little part in particular I've been talking about and sort of joking about quite a bit, and that is the magnetosphere of Venus and its lack of an internally generated magnetic field. I mentioned that doesn't mean it's a boring environment, and I'm going to let one of the scientists who are actually studying it tell you a little bit about how interesting it can really be.
Venus doesn't have a magnetic field. So Venus is just this big rock with this atmosphere and the ionosphere sitting in space, and the supersonic solar wind with the interplanetary magnetic field whacks into Venus, and it can't penetrate through the ionosphere. So the interplanetary field lines just sort of pile up ahead of Venus, like cars on a freeway. This solar wind whacking into it essentially sort of strips off the atmosphere, and it literally forms this long tail, like a comet, but stretching out into space. Pioneer Venus Orbiter was the first spacecraft to really thoroughly explore that night side region where the atmosphere is all escaping away, and it discovered this really mysterious phenomena which has yet to really be explained. Imagine that we're flying from pole to pole on the night side, so we're feeling the plasma around us, and then suddenly the ionosphere disappears, and then it sort of comes back. And this is what an ionospheric hole is. It's like a chasm in the sky, a big hole where the ionosphere is just absent. So Pioneer Venus Orbiter basically measured inside these things, and we saw that there is very little plasma, and there's all this magnetic field. And from that, they sort of suggested that this is essentially a magnetic structure that's sitting in the night side. I wanted to see if I could go looking for these things with Venus Express. What we saw is essentially this really exciting strong, straight magnetic field lines that we expected, and really boring plasma signatures. It shows us that this is a magnetic structure, right? This is a tube of interplanetary magnetic field that, well, PVO saw it coming out of the ground, and now we've seen it way out in the tail. So these things really continue out to much higher altitudes than we previously have found them at. And the other thing that's important is, well, Pioneer Venus Orbiter only saw them during solar maximum, when the sun was really disturbed and really blowy and stormy. But we've now been seeing them all throughout the solar cycle. There's sort of two explanations for what might be causing this. One possibility is that so these field lines, they come in from space and they get sort of stuck in the ionosphere. The ionosphere sort of flows from the day side to the night side, and as it goes around, it sort of meets this plasma that's in the tail, and there's sort of a pile-up between the two. So that's one idea. And the other idea is that on the day side, the field lines come in and they actually sink through the ionosphere, go through the rocky mantle, and then get hung up on this big metallic core. These field lines essentially end up draping around the core and stick out the rock at the back. One of the main differences between Venus and the Earth is simply that Venus doesn't have a magnetic field. So the way it interacts with the star is completely different. If you want to understand how did Venus get that way? Why does Venus not have any ocean? You need to understand the interaction between the star and the planet.
You need to understand the interaction between the star and the planet, and the lack of a magnetic field is a huge factor in the difference between Earth and Venus. Of course, there's some other differences, and those differences are important, but nevertheless, it's an important thing to take away from that particular note is that, yeah, we do need to actually understand the difference between these two worlds, and among the spacecraft that really want to help us, again, further our understanding there are things like Akatsuki. Akatsuki, also known as the Venus Climate Orbiter, is one that was sent by the Japanese Japanese Aerospace Exploration Agency, JAXA as it tends to be referred to as, but they had a little issue when they got there. They were trying to get there at the same time when Venus Express was in a polar orbit. They wanted to go into an equatorial orbit to actually give a bit of a different look on what's going on at the planet, and in particular in the atmosphere of the planet. However, as it was flying in, there was an obstruction in one of the valves, and they were not able to actually get into orbit at their first attempt. However, the Japanese were nice and determined, and as can only be shown in a Japanese fashion, they went and showed their determination with some nice artwork. Yeah. It's a great little view. Yes. And in fact, their determination paid off, because after 5 years, they were actually able to get back to Venus and put themselves into an elliptical orbit, which is great because it's, again, the only spacecraft there currently operating. And it's got 5 cameras to look at detail at the atmospheric dynamics, and in particular what's going on with those clouds. And while it's completed its primary mission as of 2018, again, it still has funding to continue working through 2020, which is great. And this is all well and good. What have they found? Well, among the things that were worth studying there were things having to do with the winds. As the atmosphere is incredibly dense at the surface, the wind speeds at the surface are very low, on the order of maybe 1 meter per second. Again, about that distance in 1 second. That's very slow for wind. Again, given the density of that air, that still exerts quite a bit of pressure. But if you go into the stratosphere there, you end up with a lot of high-speed winds that can go to on the order of hundreds of meters per second or even faster. And so that big disparity is really worth understanding. Why you would have dramatic high-speed winds on a planet that isn't really rotating quickly makes you start to wonder. You might think it has something to do with just the light being on one side of the planet for a good while. Maybe it's the wind going back around the other side. Well, it doesn't seem to be that simple. There's still some rotational motion involved with the directionality of those clouds. And so measuring and studying these are really important. And so we want to study not only the clouds, but Venus quite a bit more. So what has been proposed to follow up Akatsuki and all these other missions? Well, there have been a lot of proposed ideas. Here's a short list. CUVE is a CubeSat mission. Da Vinci wanted to put a sort of spherical lander down on the surface. Eve, I'm trying to remember. Envision is actually still one that is going through some planning phases. It's still competing for its actual funding. Havoc is a wonderful little dream of actually sending people there on a blimp. That's really more just a dream. Then there's the Indian mission, which I'm hesitant to try and pronounce. Shukrayan 1, maybe. And then Venera D, along with VAMP, is another mission that is, again, as you might expect, from Russia. But the VAMP side of it is one that actually is proposed coming from a U.S. company to put a lighter than air but also plane type thing into the atmosphere. And then there's Veritas and Vox, not the news organization Vox, but those are actually basically the same mission. Veritas did not win the competition, so they're trying again under a new branding with a few different things there. And then there's Visage and Vice, and not a misspelling of the news organization either. And then there's Zephyr, but with all of these different proposed ideas, very few of them have been selected to move forward beyond the proposed ideas, and fewer still have obtained the sufficient funding. The Indian mission, for example, is sitting waiting for a bit more funding to really get wrapped up and get moving. Venera D, it actually had some issues back when, it was actually started back closer to 2011. However, actually before 2011. In 2011, the Russians lost a spacecraft over in around Mars, and so some things shifted on the funding. So hopefully it'll launch sometime this decade. But yeah, okay. So what this boils down to is when are we sending another mission? I can't tell you that. Well, why should we send another mission? It's not like we can land there and have a fun time traipsing around the surface. We can't exactly go mining there or anything given current technology. Why should we go there? Well, again, it's worth understanding this world for a number of very important reasons. One really important reason actually relates back to a little side note for Venus Express, and that is, what if we're actually looking out beyond our solar system? How do we differentiate between spotting an Earth-like world and a Venus-like world out beyond our solar system? There are so many vast differences between these twin worlds. How do we actually detect them? And if we're looking at Venus, there's some evidence to even suggest that potentially for around 2 billion years, it might have been roughly habitable on the surface. So what caused this transition to absolute, absurd, inhospitable uninhabitability? If we want to actually find out these informations from distant worlds, we need to really further understand Venus. Venus is crucial to our understanding of all sorts of other worlds, because if we're looking around for the Earth and we ignore our observations of Venus, we are going to go and make many of the mistakes that were made with regards to Venus in the past. That is, it's two different objects, or, it might be lush and nice on the surface. Those clouds might be keeping it nice and cool there. There were many incorrect observations made of Venus, and if we don't use what we've learned at Venus in looking beyond the solar system, we will probably make the same mistakes again. So it is very important for us to further explore this rather hellish world. But despite being hellish, it is truly, when you look at it and consider it for what it is, not necessarily for a home, but for a place, it really is wonderful and beautiful. It really shows us all sorts of different sides as we look at it. We can see it, again, as that morning and evening star. It is nice and bright in our sky. It will be getting brighter over the next few months, too, and we can see those phases. Right now, we are actually heading past that half phase, heading towards that crescent phase, and that'll be really nice. We're getting past that waning gibbous, and so that waning crescent will be nice and beautiful, and again, it will only get brighter as it heads into that phase. And while we're looking at this place, it really offers an interesting view of a world that is very similar in many ways, but very different in others. Its surface temperatures, again, actually are hotter than here in the summer. And those temperatures largely driven by a greenhouse gas effect. It is really worthwhile to understand that greenhouse gas effect there, that greenhouse effect due to those greenhouse gases, I should say. And perhaps we should take it as a bit of a cautionary tale along the way. But it is really, when you put it all together, it really is a wonderful twin of the Earth that really is a bit evil in many ways. But in any case, it is a wonderful place. And thank you all for being here. I really hope you enjoyed looking into Venus.